On lecture one, we basically created the foundations on propositional and predicate logic. And just in the very, very basic term, a proposition is a statement which is true or false. And true or false are, we sort of, I don't know if we ever even really defined what we mean by true or false, but we defined a bunch of relations where a relation is a going back to the, so I guess what we said about propositions is that a proposition can take the values true or false and no others. And it's one or the other, it's not both, it's not some other thing. We didn't really define what is true or false, but we have some sort of sense of what it is. We defined what true or false is by sort of the tables of results of various kinds of operators. Now, an operator is a it's basically a way of building new propositions. You can take two propositions and combine them using an operator, and you get a new proposition. Things like and or implies or is equal to. They allow us to construct statements that are themselves propositions that are true or false. Okay, so I can say a lot more about propositional logic, but I'm not going to. We're going to move to predicate logic, which was the other part of lecture one. So in lecture one, we basically said that a predicate is a proposition valued function of some variables. We didn't really define what is a function or what are variables, but at least our intuition about that is that a predicate is a statement where when you substitute in a thing for a variable, which is like a placeholder, it yields a proposition. In other words, it yields a statement that is true or false. So a predicate is something that, again, combines objects and yields a proposition. Like you might say, X is an element of M. That's actually a predicate. If X has not been, if you've not said anything about X, you have to say something about X before you can actually say you have a proposition that you can say has a value that is true or false. I think I've got that right. Does that make sense to you?
First one, yeah.
Okay. Any questions on that, or should we keep going?
What's next?
Okay. What's next is we then turned to the axioms of set theory. Okay. And so for set theory, well, I would say that in another really important idea, which I'm not going to spend any time on, is that within the realm of predicate logic, we talked about what is an axiomatic system.
Okay.
And maybe that's, I don't know if that's necessarily part of predicate logic or not, but it is something that we defined in order to then move on to define an axiomatic system, which we are going to call by the short name set theory. And an axiomatic system is basically a set of predicates or propositions.
Is it a predicate or a proposition? Which one?
Good question. Let me be precise about that. So an axiomatic system, I guess the axiomatic, each step in the axiomatic system is a proposition. So an axiomatic proposition or an axiomatic system is a, are we allowed to say that it's a set? No. We can't say that it's a set or a sequence or.
No, just say a sequence, like intuitively, in the same way we didn't choose to define what a function was or a variable.
We can say that. Okay, so I won't call it a set, but yeah. I mean, an axiomatic system, the purpose of this thing is it's a way of collecting related propositions and predicates into a set of things that are the sort of the rules that we are defining, rules or statements that we are defining, like we might say, let X be a set, or let X be a natural number, which is just something we're just creating out of thin air. And then there's other elements where we're saying these are the conclusions, or these are the things that are provable in one of three ways from the set of axioms that we've defined in our system. I'm not sure I got the vocabulary right on that. I'm feeling very unsatisfied with my explanation of that.
I mean, yeah, consider that if every time we meet like this, you go through the story again, then the story gets better.
It does. Well, it also points out to me that it also points out to me that, like, wow, I had this thing totally down. And then I didn't go back and look at it. And now I'm like, it's a sequence of propositions, right? And there's three ways that you can, I mean, remember all the pieces of it, like the three ways you can either have tautology, or you can restate one of the axioms, or you can have a modus ponens, which is basically an implication of, you use the A implies B sort of axiom in order to get, you take an A and you plug it into an A implies B, and then you get a B, right? It's essentially a modus ponens. And so by using one of those three steps, you can go from one true statement to another true statement to another true statement, and that allows you to prove basically whatever you want. You can prove new. You can prove truth or falsity of statements about things that are in your system.
Yeah. I mean, whichever ones you can reach, I guess. Since
you can make, you maybe not everything, maybe not all truth, but you can certainly prove. You can make inferences essentially within your from the axioms that define your system.
Okay.
All right. So probably worth a review. There, I'm going to make a note to myself, like questions, review. All right, so come back to that for future. Okay, so and then in lecture 2, we basically took the idea of an axiomatic system and said, okay, well, we're going to define a set of axioms that form an axiomatic system. So when we started with predicate logic and propositional logic, those are essentially axiomatic systems with 0 axioms. We didn't have anything other than what we sort of established about the nature of what is true and what is false, and variables and functions. What are those? We sort of assumed those. But now in the realm of what we are going to call the axiomatic system of set theory, and we are defining a fundamental set of 4, 6, 9, I guess, axioms that that will give us this system, which will become the foundation of a lot of other things that we are going to do. Okay, so we covered, there are 2 existence axioms, which basically define, this is the axiom on pair sets and the axiom on union sets. No, I'm sorry, that's perp. The existence axioms on basically the element relation, which is that says that it basically says that without saying what is a set, it says that X is an element of Y is a proposition if and only if both X and Y are sets. And we define that as, either X is an element of Y or X is not an element of Y, and only one of those things can be true. We also define the axiom on the existence of an empty set. So there exists a set Y that contains no elements at all. So for any X, it's not in Y. That's an empty set. And those two things basically give us how do we create the existence of a set. With those two things, we have enough to say there is a thing which we will call set. Okay, and then we have another set of axioms. There are 4 of them called the construction axioms. And these, from the existence axioms, plus kind of basic logic, predicate, propositional logic, we can construct sets. And there are 4 of these. There's the axiom on pair sets, which basically says that if you have a set X and a set Y, there exists a set which contains as its elements precisely X and Y. So that allows us to take any 2 sets and make a new set out of them. So if all we had is an empty set, we can make a set which contains an empty set.
Okay.
All right. And then we have the axiom on union sets, which basically says if we have a set X, we can make a new set where the elements are the elements of X, which is a little weird, but I guess that means if it basically allows us to kind of go and do some recursion. You know? So you would say, if I have a set, well, if X is a set and it includes 1, 2, 3, 4, 5, I can then there exists a set whose elements are the elements of X. I guess it would be, I guess you would have to say X is the set of A, B, C. And if A, B, and C are sets, then you could make it, the union set says that you can make a set which is the elements of X. So it would be the elements of A, the elements of B, and the elements of C. So in other words, if X is a set of sets, you can kind of get rid of the internal braces and put all those elements in one string, and that's still a set. You've created a new set by basically collapsing the hierarchy of sets.
Like flattening it.
Yeah.
Like there's an operation on arrays called flatten.
Yeah, it's like flattening an array, or it's like saying, hey, if I've got 3 sets, I can create the union of all those sets by just putting all the elements from inside of them into a new set, right? And it's still and all it says, it doesn't really say anything special about it. It just says, hey, it's still a set.
Okay.
It doesn't say it has the same number of elements or the same number of unique elements, or that there's a equivalent set on those or whatever. It doesn't say anything else. It just says, yeah, we can union these, right? And then we've got the axiom of replacement. And this one is basically saying, this we introduced some new terminology about images and a functional relation. And so in the axiom of replacement, basically we say that how do we say this? This is something. This one's interesting because it relates to what we get into in lecture 3 about maps, right? So it's kind of important that the functional relation is. So to define that. I guess that if you have a relation between two things, between an X and a Y, then you would say that, I guess a relation is basically something that says is it just a predicate? Is it just a 2-item predicate? That's what we defined as a relation, is that a relation is a binary operator, basically. Is that right or not? Have I failed on this?
I believe that's true.
Okay. So relation is just a special name for a binary operator, like A and B, and is a relation between A and B.
anyways, but I mean, acknowledging that there may be a lot of depth here with the questions, if you have to stay on a surface level and we're forced to continue explaining, what would you do?
Yeah. Okay. So we imagine a functional relation. The axiom of replacement basically says that if you have a given a functional relation, which can translate an x into a y, right? And M is a set. If you apply the functional relation to all the elements of M, to each element of M, the result of that is still a set. And that's what the axiom of replacement is. So let's just say that times 2 is a functional relation. It's probably not a great example, but if you have the set of natural numbers and times 2 is a functional relation, applying that functional relation to all the elements of that set the result of that will still be a set.
Okay.
So it's much more generic than that, but it basically says any functional relation that you apply to the elements of to a set, to all of its elements, yields another set.
So times 2 is interesting, right? Like if you have a set of numbers and you like lambda function the times 2, then it's like a statement about how the resulting thing is a set.
Yeah, I like that, actually, the way that you use that lambda function. In other words, like if you apply a functional relation, I think that the thing about the functional relation is that for any one input, it yields one output. It doesn't yield like an infinite number of outputs.
Yeah.
And if a functional relation is essentially a black box with a 1-to-1 between the input and the output, you put all the elements of a set into it, what comes out of it is still a set. I mean, I guess because of that, for example, maybe a counterexample is easier, like, divide by would not be a functional relation necessarily, because if you divide by 0, right, then you're going to get, you're not going to necessarily have a set.
Interesting.
That comes out of it. It might be something undefined.
Okay.
Okay. So that's what I've got on axiom of replacement. I think it will hopefully come more clear what value it has as we start to use it.
I believe there's a very important thing about global comprehension and restricted comprehension.
Yes, and that is next. That's the next principle, I think. Oh, now actually, is this? Yeah, no, I guess that's right. So we have the principle of restricted comprehension and global comprehension. One second, I'm making a note on this. I'm making a note for me to go look later on something here. Okay, so the principle of restricted comprehension is to say we've got a predicate of one variable and we've got a set. And if we have so I guess what this allows us, what the axiom of replacement allows us to say is that if we have a set M and we have Y, which are the elements of M, then a predicate of one variable applied to Y, the results of that is a set. So the elements, well, I guess what we would say is the elements for which it's true. Actually, this is restricted comprehension. This is not global. So restricted comprehension says, if you have a predicate and you apply it to the elements of a set, the elements for which that predicate is true are a set.
Okay, so it's like a dot.
And would therefore be either a subset of or equal to the original set.
Okay. Would it be correct to characterize restricted comprehension as filtering?
Yes, because by definition, the results of restricted comprehension are going to be applying some rule to the elements, and you're going to be left with 0, some, or all of the elements of the set that you started with. So yeah, I think filtering is actually a really nice shorthand word for that.
Okay.
Do you agree with that? Is that I haven't heard that term used in the lectures. I don't think I remember that term being used, but that's exactly what this is doing, I think.
In my mind, I have like an association for most of the axioms to an equivalent functional programming principle. So if the union set was dot flatten for arrays, then then the axiom R is sometimes viewed as dot map or dot filter, depending on context. And then whatever, those are the main two useful ones. The other axioms are maybe not as clearly translated.
Yeah. I mean, filtering is an interesting thing because we use that that comes up all the time in the world. You know, you have a set of search results and you want to filter it.
Sure.
But I guess the thing that's also interesting is like, so the predicate is really a predicate applying to the elements of a set. There's this idea of mapping that you also like kind of hinted at in there, which is a map doesn't necessarily apply a predicate. Map function can apply any kind of a function. But when map applies a predicate and it's true or false, and then you only take the true elements, that's a filter. And that's more like in Ruby, it would be a select function.
Sure.
You know, and select is a little bit more narrow than map. So select you would use a map function to do a select. Yeah.
Okay, cool. Then what's next?
That's helpful. I like that. Okay, so next is the axiom on power sets. I mean, I guess we should say something about global comprehension. I mean, basically, what I remember about global comprehension is not sure. There's no axiom, or I mean, I guess there was a thing that we called global comprehension. I remember that it's not really valid. Honestly, I don't remember what more about it was.
Here, I'll give a quick blurb.
Give me a quick thing if you don't mind. I love that.
So there's the restricted comprehension where you say something like, give me all X. Oh, and this is where the restricted comes in. You have to say where X comes from. Give me all X that come from R where, I don't know, where X squared is equal to 0. Oh, wait, that's a bad example. X squared equals 1. So this might be like -1 and 1. The point is this is restricted because you're restricting where X can come from. Whereas in universal comprehension, you can just go say, give me all the X where X squared equals 1. And this is technically illegal. And what I mean by illegal is that the resulting thing is not guaranteed to be a set. The reason being, or the reason they chose that you always have to explain where the X comes from is to avoid a scenario where you gather up all the sets that don't contain themselves. So specifically to avoid this paradox, you have to mention where the X comes from. In this case, you can't say where the X comes from, right? And so then it's just a way to avoid paradoxes. It'd be kind of like imagining in computer science, if you had an array or something, array containing 0, 1, 2, 3, you can always go dot filter and filter it downwards. But you can never filter for a unrecognized domain, if that makes, I don't know, maybe that one doesn't make as much sense. Like imagine I did dot filter all of the X that don't contain themselves. Like that literally doesn't make sense in a way.
Filter X, not an element of X. I mean, I guess a set cannot contain itself, right?
I think there are a lot of weird things about it.
If a set contains itself, you've got that's going to cause all kinds of trouble. Like the empty set cannot contain the empty set because then it's no longer the empty set by definition, right?
Yeah.
And if a set were to contain itself, it's I guess a set can contain itself, right?
No.
No, it can't. It can contain its own elements, but it can't contain itself as an element. A set cannot be an element of itself. Otherwise, you have
it's infinitely, you know.
Well, I mean, it's fine for a set to be infinite, but if a set contains itself, you've really broken the element relation. I think you've broken the axiom, right? That because you'd say that.
Well, maybe it's just there's no way to construct such a set legally. We can say this with language, but the whole point of the axiom so far is
right. Okay. So this was, yeah, we hit, I found my thing on this. It was called Russell's paradox.
Yes, yes.
Right. So you can't say like X is, you'd say for all X is not an element of X. Well, let's see. U contains all sets not elements of themselves and no others. Yeah. Yeah, because it's a contradiction both ways. If U is an element of U, then then that implies U is not an element of U. And if U is not an element of U, it implies U is an element of U, right? There was some contradiction that way where if you posit this thing, you end up being able to prove things that make no sense in terms of the element relations definition. It violates the definition of a set.
So then
and it violates our own intuition about how you would build this thing in the world of computer science. Okay, should we go on to power sets?
Yes.
Okay, so and then I think we're pretty much done with review because we didn't cover the others. I don't think we got that far in our previous discussion. So on power sets, basically, let's see. So if M is a set, then then you can create what is called a power set, which has the elements that are all of the subsets of M.
Can you give me an example?
Sure. So like, let's just say, I'm going to give you an example. So let's just say M, so if M.
Oh, and by the way, I assume that the power set axiom does the same as the other ones and just guarantees that the resulting thing is a set.
Yeah, if M is 1, 2, 3, the subsets of M would be the set of 1, the set of 1, 2, the set of 1, 3, the set of 1, 2, 3, the set of 2, 3, the set of 1, the set of 2, the set of 3. Is the empty set a subset of M? That's kind of a weird.
It definitely is, yeah.
Yeah, but basically so you could write the set of all the subsets.
Okay.
Right.
In this case, it'd be pretty long, I'm guessing.
I mean, it would be whatever the number of permutations of 1, 2, 3, 16 or whatever it is. No, it's not 16.
I believe it would start off with the empty set and the second thing 1, second thing 2, 3, 1, 2, 2, 3, 1, 3, then 1, 2, 3. Okay, so not that long.
It's not that long, but anyway, yeah. So it's all the permutations of that, or the combinations of that. But basically what the axiom on power sets, it just guarantees that that you can write a thing called P of M, and that is a set.
Okay.
It basically means that you're not going to have some. You're not going to violate the definition of a set by creating a set of all the subsets.
Okay, makes sense.
And now, one of the things in my notes that it said on this actually was kind of interesting. I don't think we want to go into this now, but basically, there was a way that it used to be that they would use the pair sets, union sets, and the principle of universal comprehension to define the power set. And that turned out to be a bad idea, and it was instead needed to define this as its own axiom, because universal comprehension was otherwise required. So I think the reason for this is that if you have this axiom on power sets, you don't need universal comprehension.
Okay.
I'm not sure of the intricacies of what's underneath that, but that's what I got, what I heard in the lecture. Okay. All right, so that's all of our construction axioms. So there's pair sets, union sets, replacement, and power sets, and that allows us to go and pick where our starting point and then build sets. Okay, now we've got the axiom of infinity. All right, and infinity, the axiom of infinity basically says that there exists a set that contains. Oh, cool! Thanks for clearing that. that contains the empty set, and with every element Y, it also contains the set Y as an element. So it's kind of a weird, I'm not sure why the definition shifts to this, but basically if you said, I have a set, right, and it contains the empty set, and then it has a bunch more elements. And each of those elements is the set of any of the other elements. So far, we only have this, right?
Oh, and it keeps going, cool.
And then I add to this, and it's basically just saying that such a set exists. And so now I can add a new one, which would include one of its other elements, right? And it allows us to kind of keep stacking. So now I can include this thing as an element. You know, it's now.
Okay.
And so the axiom of infinity basically says that I am allowed to do this and the result will be a set.
Okay, because what to say, you could do this anyways using the pair set and union axiom, but then the idea of doing it infinitely many times is maybe bad.
Right, because it says with every element of this set, including the one that you just defined, it's still a set, right? So that's what's interesting about this, is that it actually says you can keep applying this infinitely, and the thing that you get at the end is a set. And then we name these things, like we can name these things by sort of the count of the number of the number of nested levels we have. So we can name these 0, 1, 2, 3. 4.
Okay.
And then we can define that as the set of natural numbers. Now that's really weird, but yeah.
Cool.
So there's a corollary, which is that, and basically we can define it, we can call it n, and we can say that it's a set as a result of this. Another corollary of this is that well, I guess you would say this plus the axiom of replacement. If you had a relation of, you know, minus, if you had a relation R such that R of X Y, that was defined as Y is equal to minus X. By the axiom of replacement, applying this to this set N is also a set, right?
Okay.
In other words, the non-positive numbers, so this is the natural numbers, the non-negative numbers. So the non-positive numbers would also be a set as a result of applying the axiom of replacement. And then you could.
I mean, wait, hang on. Then I'd ask you what negative means.
Mm-hmm. Yeah, we haven't really defined that, have we?
Later on, though, I get your point.
Yeah. I'm just thinking, how could you get from this to integers, right? Like we kind of just said, well, we've just defined these things as names, right?
Mm-hmm.
We can name these things. We can also get to real numbers as a power set, which is another statement that
I don't understand.
Dr. Schuler made, and I'm not sure exactly how we very simply get there.
Yeah, but I mean the transition from natural numbers to Z and then from Z to Q is explained. Then unfortunately R is not, but anyways, this is for the third lecture material. If you want to, up to you if you want to wrap up lecture 2. Personally, I don't find the last 2 axioms very, very interesting.
Okay. Yeah, that's fine. I mean, there's definitely something kind of in the underneath on this. which was, I was not clear how you get the negative numbers. This was a question I was exploring. How do you get to the negative numbers as a power set of the natural? Because he said that you can define the real numbers as a power set of the natural numbers, but I'm not sure that that's, how could that possibly be true, that you can get real numbers as a power set? I guess if the power set is all the subsets.
I mean, I believe what eventually will happen is indeed quite, it is, okay, so the reason, the step from whatever to real numbers is not explained in the lectures, but it is explained, like I went and searched it up myself pretty much, and it is interesting. And then now I can see sort of why, but explaining it is, well, first of all, I want to see, well, if you can explain the n to z and then the z to q, and then with that context then.
So z is,
oh, but hang on. Do you want to talk about this, or do you want to continue the?
I'd rather continue just to get through, and then like this would be a good one to kind of come back to.
Okay, sure.
Z is, remind me, I'm sorry, the notation slipped me. Z and Q are what?
So Z are the numbers blah 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 to -4, -3, -2, -1, 0, 1, 2.
So
yes, that's right. So it's,
and this is rational numbers, or okay, so it's integers, rational numbers, and then R is real.
exactly
right. So yeah, because he took it all the way to real numbers and talked about like sort of like a powder, like it's right, because all of a sudden now you've got an infinite number of divisions between any two things. Now, I mean, you could, if you're thinking about decimals, like you could just string together, if you know, given that you have all the possible subsets of all natural numbers, and that's also a set, and there's an infinite number of subsets, you could just imagine a, like, you know, 3, 1, 4, 1, 5, 9, 2, 6, 5, like start stringing these things together in sort of subsets. But I don't know, it's not very satisfying. That doesn't, I don't think that's what's meant here.
yeah.
There must be something more than this.
I mean, I agree. And that I think it should be, if we're talking about the S and the M, it is outside of the the M. And actually talks about the S as well.
Yeah, I think it's outside. I think it's interesting. I don't know, like you asked the right question, because like it's obviously you can get to integers by combining negative and non-negative. And here we have the non-negatives, but how do you get from this to, you know, defining a -1 or a -2? And it's something like this, but what does that even mean? We haven't.
No, that one is covered. That one is definitely covered in lecture 3.
The minus? Okay.
But here,
well,
how about
let's clear that anyway. And
yeah,
let's finish the axiom of choice, because this is one, actually, it was really important for me to touch on the axiom of choice, because it is one that I completely misunderstood the first time through.
Yeah.
And I kind of want to, I would like to just very carefully state it.
Okay.
So the axiom of choice basically it just states that for any so for any, if you have a set of elements, that there exists a set with one element in common with that. I think that's what I got from that. Hang on a second.
Personally, I find the axiom of choice and foundation uninteresting currently.
Really? Okay.
I'm sure they will have plenty of consequences later on. But
I thought, you know, I had the axiom of choice as really as something that was like, it was really doing like a lot of work for me in my thinking. But then I think I might've been just misunderstanding something pretty fundamental there, because this is where I was saying that I mean, it has to do with it ends up being useful for when you're trying to say that a vector space has a basis. You need to prove that, and basically it says that there exists a set Y which contains exactly one element of each element of X. So if X is a set of sets, then you can create a set that has one element for each element of those, right? And I kind of like that one in a way, because this does get to, I don't know how you exactly use it, but basically it says that that thing is a set, and that's all it really says.
Yeah.
You can make a set by choosing one element of each element of X.
I mean, it's called, I might as well say the point of view I have on it, which is that it is about sets where an algorithm for the choice cannot be expressed. Like, for example, if you have a set containing sets, exactly as you said, let's say that it's white socks and black socks.
Yeah. Yeah. Keep going.
And if you were to make an arbitrary selection of white socks and black socks and put them into a new set, like let's say we'll take the white sock here, here, and the white sock here, and then blah, blah, blah. And then this was the new set. The point of the axiom of choice is that even though we don't have an algorithm for picking the
even
sock,
if it's arbitrary,
yes, then the resulting set is a set, which we are not able to do unless we introduce that as a statement in our axioms.
So I guess what you're saying is that, I mean, I'm not sure how it would be complicated. Well, maybe it's not complicated. I don't immediately see how you would prove the statement that absent the axiom of choice, you cannot say that that is a set using the previous axioms. Maybe you would have to go through this, the exercise of assume you have all the axioms except the axiom of choice. Prove this is a set and say, oh, I can't. And now you say, oh, fine, we're gonna, so fine, we're gonna just make that an axiom. Because it seems like you might be able to, with the axiom of replacement or something, like if the axiom of, what if the axiom of replacement, what if you use that and you said, well, my relation is going to be, for any set X, replace that set with the first element of X. Is that not good enough? I don't know.
I think it is complicated. I have some hints that I'd like to point out, but I also acknowledge that this theorizing is interesting, but is not, or for the purpose of covering as much as we can, should not be a part of it. Okay.
Let's just, I think, leave that.
Okay.
The axiom of foundation is the last one, which is basically saying that every non-empty set contains an element that has none of its elements in common with the set.
Okay.
But I'm not sure. So I'm not sure why that's useful or necessary. That's unfortunately one that kind of boggled me. I didn't really get much out of that one.
Yeah, to be truthful, I have no idea what it's used for either. So
okay.
It is the least impactful ones, I guess.
For some other time, what is the use of the axiom of foundation? All right. So that's where we got. I mean, the stuff I actually really liked in lecture 3 is sort of what's up next, which is the classification of sets. And
I mean, hold on, we've been doing lecture 2 so far.
What's that?
Now is lecture 3.
I mean, lecture 3 was, yes, that is certainly true. The material from, and we've burned up most of our time reviewing lecture 2. Although I think in lecture 3, he's still at the beginning of it. I mean, there's sort of the boundary, but I think he spent some of the initial time wrapping up some of the stuff from lecture 2. But anyway, and so did we. Okay, so So to me, this really gets interesting because we talk about some new ideas. We talk about a space, right?
Mhm.
And we talk about when we talk about spaces, we talk about more than one. And then we talk about structure,
Preserving maps.
preserving.
But here, I actually have a list of questions pre-prepared
Oh, really? Okay.
for lecture 3.
Talk about, sure. Oh, okay. So you want to just jump into them?
Yes, I'll even copy paste them. But the starting question is, what is a space? That is
right. Okay. So right. So a space is a set that is equipped with some structure. But what do we mean by that is a good question. I mean, topology or differential or group theory or whatever. These are spaces, but those are the structures that would equip the space.
Okay.
Right. But so if a set, so when we say that that we have this recurrent theme, which is the classification of spaces by means of a structure preserving map, right? You have to have a sense of, well, what does structure mean in order to say whether or not it is preserved?
Okay.
So the structure of a set would be I guess it would be the
But you do attest that a space is just a set equipped with structure. Is that right?
Yeah, absolutely. Yeah. The space is a set equipped with some structure. But then if I ask the subsidiary question, okay, well, what do I mean by the word structure?
I mean, it's
we can talk
set,
about,
right?
It's what?
It's going to be a set, right?
Sure. Yes, it is. Well, I mean, so a space is a set, and it is a set that has some structure to it, right? What do we mean when we say structure, though? I mean, we can say that the structure, we can talk about it being.
What are some examples then of structure?
Well, let's see. So I'm trying to think about this because I mean, I have all this stuff about, well, what does it mean to preserve the structure, right? Like a structure preserving map is bijective, right? Or bijection, right? So that is a map from A to B where well, let me actually go this way and then see if I can back my way into the definition. Would that be all right? Or is there something here that you want to go after?
I think it might make sense to just continue asking questions and then to revisit this question in like 15 minutes.
Okay, great. Let's do it.
So in the lecture, it says that sets are a space. How come?
It's how come?
Yeah, that sets are an example of a space. Is that like, do you have any comments on that?
So I guess I mean a set is a space. What is? I'm sorry, that question is really throwing me for some reason. We defined a space as a set equipped with some structure, or a space is usually meant to be a set that's equipped with some structure. But you're asking sort of why?
It's a bit of a trick question. The idea is that the structure that is equipped with a set is the empty set. So a set is a space in the sense that it has no structure.
Wait, a set is a space that has no structure? I'm sorry. I did not follow that at all. I'm confused. Okay. Try that. Can you try again? Just restate it again. Let me think about that.
here. So if a space is set plus structure,
Mhm. Yeah.
and then in the lecture, it just states, it says that sets are a space because it is just the set equipped with the structure that is the empty set. It is being, purposefully,
Sure.
yeah, they're just saying, oh yeah, a set is a space because it's the space that doesn't have any structure.
Okay. Does that mean that a set is a space? Or is it that a space is, I guess a space is some set, right? So a set is a space.
I guess, yeah, the letter X that can stand for any sets is space.
Okay. Okay, so sure. So you can have a set, and a set is a space. And you can have a set that has no structure, and that is a space. And
What are some examples?
And you can also have a set that does have a structure, like a structure. I mean, would a set that has a structure be something like, a set that has 10 elements? That is a structure of a set. No, or a set where each element of the set is a
maybe one thing that will help here is if you can enumerate some examples of spaces.
Okay. Examples of spaces. Well, I mean, you'd say like natural numbers would be a space?
Okay, so natural numbers, but then to what degree? Natural numbers equipped with nothing, equipped with addition, equipped with...
Oh, I see. Well, so are operations like addition, would that be a structure?
Hell yeah, 100%.
Oh. Okay. So a space, so a structure could be a, yeah, so that's, I was thinking of a structure as being almost like an axiomatic set or an axiomatic system. But
I mean, you were totally right when you said that things like addition, multiplication, or a topology are all examples of structure.
Yeah. I mean, topology was just like, that was in my notes, but I don't know why that counts as a structure, right?
Yeah.
And I'm not really sure. I actually I think what I'm running into is that honestly, I can see what it means to preserve a structure. If you give me a set and say, or if you give me a space and here's a transformation that's going to, or a map that's going to preserve its structure, for some reason, that's not hard for me to get. But then saying that, like in the abstract, like, well, what is a structure? Really threw me. But
Yeah.
if we can say like, and this is where like it feels like that's kind of I'm not sure why this is such an obstacle for me. Damn. That sounds like that should be such an easy question. And
I mean, for context, I was also stuck on what a space was for like a little bit of time, and then eventually it clicked.
Yeah.
So it is like,
okay. Well, I mean, so obviously there's something there for me to go and dig on, really. Geez.
okay, but yeah, that can be for another time.
Yeah. So why don't we leave that?